Okay, let's figure out how to find a Maclaurin series for f of x given as the integral from 0 to x of e to the negative t squared minus 1 with respect to t. I think for explaining purposes, I am going to take this integrand here and just kind of say, you know what, you're just some function of t. So we'll keep track of which function of t it was, however. So if we do that, then what that means is that we could think of f of x as the integral from 0 to x of this g of t dt. So if I can figure out what the antiderivative of g is at x, and then subtract off the antiderivative of g at 0, then I'll be done with f of x. So master plan, figure out what g of t is in a Maclaurin series form, and then take its antiderivative, plug x in, plug 0 in, subtract them, be done. So that's our plan. So a lot of the work is going to be on just figuring out what g of t is in Maclaurin series form. To get started, we're going to look at the power series for e to the x. And I hope you do have that one memorized. Okay. All right. So here's enough terms, beyond enough, I would say, to establish the pattern for e to the x. And then if you have e to the x, then you should be able to get e to the negative t squared just by substituting negative t squared in for all of the x's. So on the left side, after that substitution, I would have e to the negative t squared. And on the right side, I would have 1 minus t squared plus, so if you had negative t squared squared, let's see, and then we'll end up with a negative t to the 6th, I think, over 3 factorial, and then positive t to the 8th over 4 factorial, and then the next term would be negative, and we could continue in that manner. Okay, so what do we need to do next to this expression to get actually g of t? We would simply need to subtract 1 from both sides of the equation. So I'll subtract 1 from the left side and subtract 1 from the right side. Okay, so on the left side, I'd have e to the negative t squared minus 1, which I claim is g of t. And on the right side, those 1's would cancel, so you're just left with all the t terms. There we go. Okay, so remember, once we have g of t, remember what our master plan is figure out what's the antiderivative at x, what's the antiderivative evaluated at 0, and then subtract those things. So before I get antiderivative with respect to x, I think I'll just minimize the amount of thinking that I need to do, and I'll just do the antiderivative in terms of t. So we would get the antiderivative of all the terms plus a constant of integration. So I'm just going to go ahead and put that first. We always put the constant of integration first, so it doesn't look like you're going to add infinitely many of them at the end. So let's do antiderivatives. So just power rule. There we go. Okay, now that we have that, we could figure out, well, what would this be with x plugged in? And that would simply be the exact same thing, just with x's. And you can definitely see some steps here that you could, I'm sure, skip, but sometimes just a little more writing actually makes you move through things a little bit easier. Okay, so there you have the antiderivative with x plugged in, and now let's go ahead and look at what would it be with antiderivative with 0 plugged in. Well, you'd be plugging all the 0 in for all the x terms, so anything with an x in it would vanish, and you'd just be left with c, which is what you kind of would have predicted already with an integral with bounds. The constant of integration would subtract out, and so if you were to subtract them, what would you have if you subtract the antiderivative evaluated at x and the antiderivative evaluated at 0? If you look up at our master plan, you would have your rule for f of x. And then on the right side, just let the c's vanish, and then what you have left is your answer. Oopsie. That should be a 7. Okay, and then one thing I also want to mention before I call it quits on this problem, first of all, this is a perfectly fine answer. Answering in expanded form is a-okay. But let's talk about how to write this answer in sigma notation, because it is so doable and so easy. I don't want anybody to think it's hard. I've heard that some people are checking their answers in the back and a little discouraged that things are in sigma notation sometimes. So let's address that. So if you look at the patterns and you just try to write a rule that would generate these terms, I would first notice that the signs start out with a negative, then go positive. So use an alternating rule, and I'm going to go ahead and use -1 to the n. And then I'm going to think, okay, well, what would I have to have n start at to make it start off on a negative, then go positive, then negative? And I claim that n equals 1 would accomplish that. And we'll go ahead and put that infinity up there. Okay? And then now let's figure out, okay, well, what would you have to do to a 1 to make it be a 3? And then you'd want a rule that would then turn a 2 into a 5. And so I claim that the next part of the rule would be x and then to the 2n plus 1. And let's just see if that works. If n is 1, do you get 3? Yes. If n is 2, do you get 5? Yes. If n is 3, does it give you the 7? Yes. Okay. Now for the denominator, I'm going to go ahead and put back here, I'm going to go ahead and put x at 3, I'm going to put a 1 factorial. So it's really easy to see, oh, okay, well, first term, second term, third term, fourth term. So the little factorials are just, you know, whatever term you're on, that's getting factorial there. And then the 3, 5, 7, 9, well, we already wrote the pattern up here for that. So you could just say quantity 2n plus 1, and that would generate the 3, 5, 7, 9. There you go. And so if you check your answer in the back and they have it in sigma notation, now you know a way, hopefully, to always take your term by term stuff and then just kind of write the pattern for the rule and put that into sigma notation.